Hello everyone, in this video we will go through with solving examples. Example 6.4. Let's read together. Air at 1 atmosphere and 20 centigrade degrees flows with an average velocity of 10 meters per second through a pipe having a diameter of 25 centimeters. Some properties of a flow is given and we are aiming to make a model of it. A model of this flow is to be constructed using water as flow medium. Please note that in the prototype we have air, but in the model we will have water. What must be the average water velocity in a 6 centimeter diameter pipe if the flow is dynamically similar to the prototype? So let's write down what we know, what are given. Initially, these are given to us. We have a prototype. Air is in the prototype, so that the viscosity of the prototype is the viscosity of air, which is given here. And also density of air will be density of the prototype. And the velocity is given, and also we have diameter given. Diameter of the prototype is 25 centimeters. It's a pipe flow, and the velocity of the prototype is given as 10 meters per second. We are aiming to construct a model by using water, so that viscosity of the model will be viscosity of water density of model will be density of water. Diameter of the model is selected as 6 centimeters and is asked to calculate the velocity of the model. What should be the velocity of the model? Let's initially calculate this first part. Please note that it's a pipe flow, and in order to have dynamic similarity in the pipe flow, we need to have Reynolds model. This means that Reynolds ratios of model and prototype should be equal to 1. This means that Reynolds number is VL over or VD for pipe over nu, so that velocity ratio multiplied by diameter ratio over viscosity ratio should be equal to 1. So the diameter ratio is to be calculated from here, and viscosity ratio can be calculated from here. Let's calculate. Diameter ratio is diameter of model over diameter of prototype. And viscosity ratio is viscosity of model divided by viscosity of prototype. From here, velocity ratio, which is nu r divided by dr by this Reynolds model, will be equal to I didn't calculate this, but I can calculate easily. Zero point 0.0662 over 0.24. equals 0.276. And from here, as velocity ratio is obtained and we know velocity of the prototype, we can easily calculate velocity of the model, which will be equal to velocity of prototype multiplied by velocity ratio 10 multiplied by this equals 2.76 meters per second. This is the first part. And note that there is also a second part of the problem. It is asked that if the pressure drop in the model, let's call it as B, if delta P in the model is given as 200 kilopascal, what will be the corresponding pressure drop in the prototype, delta P in the prototype? In order to calculate this, we need to find out pressure ratio by using Reynolds model. Pressure ratio, without knowing anything, can be obtained like this. It is, by definition, force over area, so the force ratio divided by length ratio square will give us pressure ratio. For force ratio, we can write mass ratio multiplied by acceleration ratio, and mass can be written as rho times length cube, and acceleration can be written as length divided by time square. And note that time equals LR over VR, because L over T is velocity. So by inserting all those and making the simplifications, PR will be equal to rho R. There will be VR in the calculation. Let me check. Yes, VR square divided by LR square. Here we need to make a correction. This is not VR, but let's do it together. This TR should be TR to the -2, not +2. Please correct. And we have, instead of TR, we will write LR over VR, and for VR, we will write nu R over dr, or we can just write this number. It is not very much important. And please note that this dr is already LR. The one we call as LR is also already dr. So that rho R, LR to the power 4 divided by LR square TR square. For TR, write down this, which happens to be LR square over nu R. Rho R, LR to the power 4, nu R square comes from bottom. LR square cancels. So LR to the power 4, this one. These two cancels each other, and we have rho r nu r square divided by Lr square. And inserting all those that we know, rho r is already known, although we didn't calculate it. Let's calculate initially that one. Rho r is rho of model divided by rho of prototype, which is 1000. 1000 divided by 1.21. This is rho r, and PR will be equal to nu r, already calculated here, 4.0662, and LR was 0.24, gives us PR equals 62 and 93. It is said that pressure at the model is given and prototype is asked. Please note, pressure at the prototype equals pressure at the model divided by pressure ratio. Gives us 3.18 kilopascal as the result. Okay, that's it for this problem. Let's go through with the next one. This is also related with modeling. And we have water discharges into the atmosphere from an orifice on the side of an open tank. A small model of the tank is to be built using water as the flow medium, so that we have the same fluid. If the scale ratio of prototype to model is 10:1, so that LR is 0.1. What are the ratios of discharge and force exerted on the tanks at dynamic similar conditions? And please note that although we have dynamic similarity, here we have an open structure, open tank, and we have an orifice and discharging out, so that we don't have Reynolds number important anymore, but we have fruit number important, so that we need to use fruit model. And fruit model will be used, fruit number equals V over GL, so that fruit model gives us this GR LR LR in square root, and GR is always 1 because we have the same gravitational conditions. This fruit number should be equal to 1 in both cases, or the ratios should be same, which gives us VR equals LR in square root. So that this will be our base equation to use. Let's see, it is asked to calculate ratios of discharge and force. Note that discharge is velocity multiplied by area, which is length square. Instead of VR, we can write down this LR to the power 1 over 2. this gives us this number as the discharge ratio. And for force ratio, please note that force is mass times acceleration, and mass is density times L cube, and acceleration is L divided by T square. And let's also write down here again, TR equals, LR over VR, and here as well as VR equals in square root LR, TR also equals to in square root LR. So that this becomes rho R is again 1 because we are using the same material. LR cube, LR is LR to the power 4, and we have TR square, which is LR square root to the square, will be equal to LR, which will be equal to LR to the power 3, and this equals to 0.001. Okay, this will be force ratio and this will be discharge ratio. Let's go through the last example in this chapter. We have a spillway. We have a spillway for the dam, and the width of the spillway is given, and the discharge that it is carrying is given at float stage. A model is to be built with 1 to 15 ratio. We are asked to calculate width of the model, surely and very easily, as LR equals 1 over 15, and width of the prototype is given as 20 meters. Surely model width will be this multiplied by 1 over 15. Is equals 1.33 meters. Also, it's asked to determine QM, and please note that again here we are using the fluid model because it is again an open structure, open atmosphere. And from previous example, we can use this. Please note, if you have fluid number, QR equals LR to the power 5 over 2, which equals 1 over 15 to the power 5 over 2, 1 over 871.4, and QM will be equal to just QP times QR. From here, QM will be equal to 0.143 meter cube per second. And it's asked to calculate operating time for the model corresponds to 24-hour period in the prototype. Already we used fruit model, but it is said that neglect viscous and surface tension effects. This means that do not use the models that are giving more importance to the viscous and surface tension, viscous force and surface tension forces, so that we are using fruit model. TR equals LR in square root. Recall from previous example. Numerical value will be like this, and the corresponding time in the model will be time in the prototype multiplied by the time ratio, 24 multiplied by 1 over 8.87, from here, time in the model will be equal to 6.2 hours. Okay, that's it for the example. I hope you understood those well.